consider this 60 kilogram person traveling, show side information, 5 meters per second towards the ramp. Once he gets towards the ramp, he's going to convert his kinetic energy into potential and he will ascend the ramp. Okay? He will be doing work against gravity. He'll be storing that energy. So at the start, we make the statement that E total, EP plus EK plus EF. Well, we're saying he hasn't lost any energy yet, and he's got no potential energy because he's on the ground. So his total energy is a half mu squared. So he has a total of 750 joules of which he can do work with. Right. Now, we've got S. What we're going to get here, we can determine H quite easily, but we could express S. Would you mind shutting the door for me, please? Well, H equals S sine theta, so S would equal H divided by sine theta. So really, we've got to sort of stop halfway and figure out what H is, or we could just throw in S is H on sine theta. Oh, sorry, H is S sine theta and then solve. I'm getting a little bit bewildered. All right, at the finish, so that was at the start. At the finish, we can say E total equals EK final plus EP final plus EF. Again, we are going to assume no friction for now. We're going to assume that he is stationary at the top of the ramp, and then we can say that equals mgh or mgs sine theta. And all we're solving for is S. Running a little bit out of room, I could then say S equals E total divided by mg sine theta, and that would give us the length that he has travelled. 750 over 60 by 9.8 sine 15 gives us a length of 4.93 metres. Okay? Correct. What I'll leave here, could you just write, and you're going to solve this in your own time. Suppose he only gets to S equals, so in a perfect world, he could travel 4.93. Let's let friction rear its ugly head and say that he gets a little bit less than 4.93. Let's say he only gets to 3 metres. What I would like you to determine or calculate your energy lost to heat and friction, and then the force of friction that must have been acting. Okay, I'll let you ponder that for just a moment. Yes?
Are we assuming that friction is the
Yeah. So obviously we don't care about him here. We only care about him. Are we going to do this again? What hideous beast will I have created now? Okay, so there he goes. We only care about it when he gets to the ramp there, absolutely. So we'll find the average force that acts. Next question. I'm going to show you here that mass doesn't really matter. What you'll see is that there will be an M term on both sides of the equation. So let's figure out Tarzan, he's running along 10 meters, grabs a vine rope. In doing so, he's converting his kinetic energy to potential energy. What we are going to say is that the sum of all energies initial is going to equal the sum of all energies final. We could then say mgh initial plus a half mu squared equals mgh final plus a half mv squared. Now some of these terms will cancel. For example, At his highest point, we make the assumption v equals 0, and that's going to enable us to cancel out that term. At his highest point, he has no kinetic energy final. We can also make the assumption that h equals 0 at the start, in which case we can cancel out that term. And it simply becomes a half mu squared equals mg h final. And this is where I can cancel out the mass. Okay? Even though I had given you his energy, or so his mass as 90 kilograms, we didn't have to find out how much energy he had at the start. We didn't have to find out how much energy he had at the end. We're almost skipping those two interim questions and going straight to the final, how high up does he ascend? And we can rearrange. H final is a half u squared over gravity. And it becomes a very, very simple, a half of 10 squared, 50 over 9.8 gives a height of, I don't know, 5.10 meters. Obviously, if there was a part A, find his total energy, well, yes, we would need to know his mass and we would express his total energy in joules. Okay? But again, given this scenario, the final height that he rises to depends only on two things: how fast he runs at the Tarzan rope and the gravitational field that he's in. If he ran at the Tarzan rope on the moon, he would rise 6 times higher, because gravity on the moon is 6 times weaker. He would be able to traverse 6 times higher. He would still have the same energy, but it's in a weaker gravitational field. So you need to be higher up to store the same amount of energy. Okay? So again, I like to put in questions in year 11 and 12 where you're not given the mass, and it forces students to, rather than evaluate each step, how many joules, how much height, you almost have to leave it in that general form. And then from this step, which I will highlight right now, from that step, you can simply show that mass is not a factor. Another thing to think of is you could have a little midget running alongside him that was a half of his mass, little midget and Tarzan, and providing they both run at the rope at the same speed, they will both ascend to the same height. Doesn't matter that one of them has less mass than the other. Okay? Efficiency, gentlemen. This one's pretty simple. Your equation, it's a ratio of how much useful energy is produced in an energy transform. And I'm about to tell you, you'd never get all of the energy out. You're always going to lose some energy due to heat and friction. Okay? So whatever the energy transformation is, you're always going to lose energy. We're going to use a squiggly E for the symbol of efficiency. And it is a percentage, so we're going to just convert that decimal or fraction into a percentage. There are some other equations. You could have power out over power in. Since power is energy over time and your transaction is happening in the same time, the t's will cancel. You could do E over T over E over T. Those t's would cancel because they're the same time value, so they're common on both sides of the numerator and the denominator. So you can look at power, how much effective power you get out of a car engine versus how much chemical energy you're transferring. You could also say, instead of saying energy out, you could say energy useful over energy total. Right? And the easiest example is given below. Your incandescent light bulbs are incredibly inefficient. We want them to make light so that we can see in this classroom. We do not want them getting warm, okay? Maybe in winter, we might want the heat. Ooh, it's cold in here. Turn the lights on. Ah, that's nicer. No, that's not what we use a light bulb for, okay? So you've got to look at what is the required, those urns at the back there, we want them to make heat. So their useful energy is heat. Even though they're making bubbling noises, even though they're moving the water around, we don't want the water moving. That laptop, we want it to only make light and sound, but it's also going to be making heat. Okay? An engine, we want it to make kinetic energy, but it also makes sound and heat. So you've got to consider the object, decide what it is. As I said, it is not possible for a transformation to be 100% efficient. Your out energy is always going to be a little less than your in energy. You are always going to lose some energy. Okay? It is not possible for 100% efficiency. Our poor little incandescent light bulb. Incredibly inefficient. Edison, when he made it, this was the easiest way to make light without needing oil or coal or candles. Let's figure out how much useful energy is produced. Whoop, didn't mean to do that. Try again. So that's our energy out. Now hang on, we don't know our energy out just yet. We've got to find energy total. So the total power of our light bulb, 40 watts, multiplied by time in seconds, 10,000. That's going to be 400,000 joules. Now, here, you're going to hate me. I'm going to just move this over. Go back one page. I don't know what that's doing. Okay, thanks. It's telling me stuff. The computer's talking to me. Are you seeing this? Yes. Okay. Now, students attempted. You could solve this answer in your head. What is the answer?
40,000.
40,000. What did you do just then?
I multiplied by 0.1.
Yeah, you found out 10% of that number. And you'd be correct. But you'd lose marks if you just wrote down 40,000. You've got to use the entire equation. Okay, it seems a little bit silly, but we're going to say energy out over energy in times 100 Again, obviously, you could evaluate it you could put the numbers in after this step. You could have put in 10 equals E out over 400,000 times 100, but you would still be making those same operations. You'd be dividing by 100 and then multiplying by our 40,000. So 10 times 400,000 over 100. As Marcus correctly said, you're multiplying your 400,000 by 0.1, you get 40,000 joules of useful light energy. Okay? For this one, again, you're going to do some maths in your head. Oh, I put 400 in, I'm losing 360,000. That is the correct answer, but you've got to write it out as a statement. So our energy total, we'll say that's I'm not going to use light. I'm going to go kinetic energy plus, my laptop is struggling, plus E lost to heat. Or we could write here E lost. Therefore, energy lost is our total minus our light energy Okay. And that's pretty much it for conservation of energy and efficiencies. We'll just quickly go back. I would like you now, if you have the room there, try and think how you might solve. Again, If he gets to that, we can still make the assumption at the highest point, which it turns out to be 3 meters up the ramp, he's still stationary. So you can still cancel out the kinetic energy at that point. You knew the total. You can now find out his potential energy. You can now find out how much energy he's lost. Okay? Yes? What? Is it not 4.93? Are you trying to tell me that 750 over 60 by 9.8 sine 15 does not equal? Rookie error. Rookie error. It was in radians on his calculator. So, gents, I'll leave you to ponder that. I'll